In the name of God, the compassionate, the merciful. Engineering Plasticity, Chapter 3, Yield Criteria, Part 6. We have been talking about the yield criteria during the past sessions, and here I'm going to discuss the yield surface. As you can see in this figure, and as we mentioned before, the yield surface could be either concave or convex. That's convex, that's concave, and that's convex. Okay, this is convex, this is concave. Concave and convex. And now in here we want to know which one of these is really the yield surface, and could it be either concave or convex, or only one of these is possible. So that's what we are going to discuss. In order to do that, we have to discuss first some ideas like the Hill's stability criteria. You can get it from this reference, 1958. As you know, Rodney Hill was the scientist which set up the most of the basic ideas and concepts in plasticity. He is very famous, and he was a genius, really. He was a mathematician and also a mechanical engineer. And this paper in the Journal of the Mechanics and Physics of Solids sets up the idea of stability criteria. Later on, Drucker stability postulate was developed by Drucker, and we are going to discuss these in order to understand the yield surface. So this is the title of the subject that we are going to follow: normality, convexity, and material stability. So from this title, it appears that the yield surface must be convex. We are going to prove that it's a convex, and we are going to prove the normality and explain what it is. Okay, first we discuss the material stability. Now this figure should be very familiar with you. This is a pencil which is set up here on its bottom. Here it's set up on its tip or top, and here it is laid down on its side. Now, if we apply a force like that, we get a delta x, which is displacement, and if we increase the force and get a delta x, and then release the force, the pencil comes back to its original place. Of course, if we apply a large force, it won't come back and fall down. But supposing that we apply a force such that we get a displacement, a small displacement, delta x, and after we remove the force, the pencil comes back to its original place. So we say that it's stable. Now this one, clearly, the smallest force that we apply, it will fall down. So we say it's unstable. It won't go back to its original place. So stability means that, in this case, it means that if you apply a force and then remove the force, it comes back to its original place. We call that stability. What happens here? If we apply a force, it will move delta x, but it would not come back to its original place, and it will not change the position, because this is the position and this is another position. When we apply the force here and remove the force, it comes back to its original position. This will change, the original position changes. But the original position here is like that. So if we move it here, it just have a displacement, but the position has not changed. Okay, so that's why we call it neutral, because applying the force on this one does not make any changes. It makes some changes, it moves it delta x, but it does not, it neither goes back to its original position nor will it be completely out of balance like this. So we call this first order stability. Okay, first order stability, and we have shown it in this figure here. The first one is this, the first position, stable position, and we show it with like that. F delta x is positive because this is work, in fact. F delta x, force times displacement is work, and this work you apply the work and it will come back to its original position, and we show it with this curve like this. Okay, that's force, and that's x, that's displacement, and that's force. So if you apply the force, increase the force, you get some displacement, and when you remove the force, you come back to the original position. The neutral case, clearly it doesn't make any difference. I mean, if the force is constant, and if you apply constant force, you get a displacement, and if you remove the force, it doesn't make any difference. Here is the unstable position. Look, we got this force in here. Here force is decreasing. See? So it means that as soon as you apply a small force like that, it will have a large displacement, and as we have the displacement, the force also decreases. So here we have shown that we got a negative value. Of course, work is never negative, but here we are just showing that how it's changing, because we have decreasing force, so we show it with a negative value, and we have increasing displacement. Here we have increasing force and increasing displacement, that's why it's positive. Obviously here we don't have any increasing force, but we have displacement, so no change, and that's why we have put it equal to 0. So these are three conditions for the stability, and we call it first order stability. Okay, because we can find out just with the value of f and delta x. If it is positive, it's stable. If it is 0, it's neutral, and if it is negative, it is unstable. How do we apply this to the real material? I will show you in a minute. Okay, so this is the case for elastic deformation, where the forces are dependent on deformations. In the elastic case, it's like a spring. If we apply a force, we get a displacement proportional to the magnitude of the force. Okay, so that's why we could find out whether it's stable or unstable very easily. First order stability. Now, here we are going to explain the second order stability. If we apply a force opposite to this, like friction or anything else, F prime, if we apply F prime here, then for all of these cases we have positive work, because this F, when is applied against this F prime, it is dissipated, and so we have F delta x is greater than 0 for this one, for that one, and for that one also. obviously if we apply enough force to overcome that, then it will fall down, this one. And if we apply enough force here, this also falls down. But we are not talking about that condition. We are talking about a small force applied here. We have an opposite force, so that this is it cancels out with this F prime, and this was positive for the first order stability. It is also positive for the second order stability, because we have applied an external force in here that we call it second. Now, obviously all of these are positive now. Okay, they are positive because this doesn't fall out, because this F prime keeps it in place, and this F only cancels with this F prime, and we must increase F big enough to overcome this and to make this fall down. But we are not doing that. We are just applying a small force and an opposite force here, so it keeps it in place. So it's positive also. But it is not in a stable position. It is in an unstable position clearly, because if you apply the force a bit further, it will fall down. So how could we distinguish between these three? Because with the first order stability, all of these is positive. So how do we distinguish between these? The question would be, how do we distinguish these three cases from each other? Here you can notice that we have the same curve as before, F versus X, but here, because we have this F prime, the curves become like this. You see, this is the stable case, this one, which as we increase the F, we increase X, so F delta X is positive. The second one also is the same thing, and the third one also the same thing, because we have this F prime in front of this F resisting any of these, so the value of F delta X is positive for all three. So the question is, how do we distinguish between these three? Now the answer to this question, what was the question? The question would be, how do we distinguish these three cases from each other? The answer is given by examining how the work gradient changes. Okay, that's the second order stability. If the work gradient increases, then there is a stability, and if it is zero, it means neutrality, and if it is negative, there exists an instability. So work gradient, what do we mean by work gradient? Second order stability, we mean this. Instead of F delta X, we say delta F delta X. Delta F delta X, delta F delta X. So we examine these. If this is positive, then we say there is a stability. If this is zero, we say it's neutral. And if it is negative, we say it is unstable. So for such a case, when we have these external forces applied, then and in opposite directions, then the first order stability doesn't give us any clue as to which one is stable and which one is not stable. And only the second order stability, these equations, tell us whether this is stable or this is unstable. So let's see how does it apply to real material. Okay, material stability. Now this is the stress strain curve, and we have here the elastic part. Here we have the plastic part, but the plastic part here obviously is strain hardening here. Here is a strain softening here, and we want to know how this Drucker stability postulate is applied here. Now, for the elastic deformation, which is this part of the curve, we have work is equal to sigma delta epsilon. Okay, that's the A to B. Supposing we move A to B, we want to know whether it's stable or not. In the elastic part, it is easy because we use the first order stability. and just delta epsilon times sigma. Okay, for the elastic case, sigma is less than sigma y. Therefore, when loading elastically and unloading, there will be no work done. It's a closed cycle. When we go up here and release the load, we go back. As a matter of fact, it is a fundamentally known principle that there is no work done on a closed cycle. Okay, hence here, as mentioned before, there applies only the first order stability conditions, since after the unloading there would be no work released. So from moving from A to B or anywhere along the elastic line, sigma d epsilon is positive. Clearly here is positive. Okay, now then let's see what happens if we move further into the plastic deformation. If we go to the plastic deformation for plastic case like A prime, therefore when loading plastically there is a permanent deformation. The work is mostly dissipated as heat and some stored in the lattice. We know, we have mentioned before in the introduction, that when we apply a force and we produce permanent deformation or plastic deformation, the energy is dissipated. More than 90%, maybe 98% of the energy which we apply to deform the material is dissipated as heat, and only 2% or 5% of that energy is stored in the material, in the lattice structure. It is applied to change the slip planes and make the planes slip and move the slip systems. Okay, only 5% or 2% of the energy applied at the material is stored, and rest of it is dissipated. Okay, so that's what we are saying here, dissipated as heat and some stored in the lattice. So when we are at point A prime moving to B prime or moving to A zagon, this kind of things happens. Now let's have a look at here. Now here, because we have moved out from the elastic region to the plastic region, the first order stability doesn't give us, doesn't tell us whether it is stable or not. So we have to use the second order stability. And second order stability is this: delta sigma, delta epsilon, whether it is greater than 0, it's a strain hardening. So it means that as you move along the curve, you have to apply more sigma, because this delta sigma, delta epsilon is greater than 0. Okay, so that's the strain, as we call it, the strain hardening. The material becomes harder as we go along the path. And the neutral case is where is this place, A triple prime. Okay, that is where here delta sigma, delta epsilon is 0, because it's neither strain hardening and nor strain softening. It's a stability point at the top. Okay, it's where the necking starts, start of the necking, end of the strain hardening. So here we have a neutral point, which is no strain hardening, and from this point onwards the material softens. In other words, sigma decreases as we have more deformation, more plastic deformation, and decrease in sigma. So we have decrease in sigma, and this is negative. So that's a strain softening. Okay, so that's how we apply the Drucker stability postulate to the material. That is our understanding of the material behavior in the elastic region and in the plastic region. Now let us further discuss this matter, and here we have this material which has a elastic part. Supposing we have this sigma A in the elastic region and we have this sigma B in the plastic region. So we have moved from sigma A to sigma B, and that's the epsilon, and that's the change in deformation. Okay, up to this point it was linear, and to this is a strain hardening. Okay, let's see what happens here. Now we can write down, moving from sigma A to sigma B, the work done in one cycle of elastic plastic loading from sigma A to sigma B. We have this elastic loading and this plastic loading. Okay, so we have here sigma B minus sigma A, sigma B minus sigma A, d epsilon P, which is this part, this green part, the epsilon P. That is the work done. And also moving further into the plastic region, we have to apply d sigma to the sigma B. Yeah? D sigma to sigma B. So we have d sigma d epsilon P for this part. And so we could call this W1 and we call this W2. And you can see here again the two parts of the stability postulate, the first order and the second order stability postulate like this, applied to the material. Yeah, for moving from A to B, sigma A to B, we have the first order stability, and the second order stability we have in this here, where we have moved just d sigma and the epsilon. We get the second order stability, and this is the first order stability. Because we are in the strain hardening region, this must be positive. But if we go to the UTS, ultimate tensile strength, then that would be 0. And when we move outward from the point of stability or UTS, then it will become unstable, and this becomes 0, minus, negative in fact. Okay, so that is our understanding of the stress strain curve and the elastic plastic deformation.